Hello everyone, my name is Trevor Frisby and I am a PhD student at Carnegie Mellon. Today, on behalf of myself and colleagues Jiyun Gong and Chris Langmead, I'm very excited to speak with you all about some really cool work that we hope will change the way you look at traditional experimental science. My talk is titled Asynchronous Parallel Bayesian Optimization for AI-Driven Cloud Laboratories, and I'd like to start by describing the long-term motivation behind this work. And that is the automation of large-scale closed-loop science and experimentation. This diagram shows a generalized version of the scientific method. We make hypotheses about a system of interest, design experiments to test them, run experiments, then update our hypotheses. You can see that it has this closed-loop property, where the output of one stage provides the necessary ingredients to fuel the next. However, I think there are two challenges that are often faced when moving through this cycle in a traditional academic research setting. The first is inefficiency, let alone all the issues associated with actually conducting experiments. Each arrow in this diagram is also a place where some decision-making process must take place, such as interpreting data and choosing what to do next. We can begin to address these issues by introducing machine learning and automation at each of these steps, using artificial intelligence to avoid halts to progress. The second challenge is the availability of resources and experimental equipment. This is where the Cloud Lab shines, and I'd now like to take some time to describe what exactly a Cloud Lab is and why it addresses both of these issues. A Cloud Lab is an ideal environment for performing closed-loop science and has two principal components. The first is a real-life experimental laboratory. What separates this lab from others is its size and the scope of all experiments that can be performed within it. Existing cloud labs are able to support over 100 different types of experiments, many of which are fully automated and carried out by robots. The second component is what makes the cloud lab so powerful, and that is the interface through which a researcher uses the lab. In the cloud lab, experiments are executed by writing computer programs that specify which experiments and procedures to carry out. This allows you to impart conditional logic on your experiments, where you can automatically choose successive actions based on previous results. Importantly, you can run experiments in parallel, which can provide a level of throughput that would be otherwise unattainable. An apt analogy is that cloud laboratories are to regular experimental labs as a high-performance computing cluster is to your standard laptop. These lead to a number of benefits to using a cloud lab, including wider access to materials and instrumentation, improved reproducibility, and savings in time and cost. These lead us to anticipate that cloud lab usage will increase across industry and academia alike. While I believe that cloud labs provide the potential that could one day lead to true robot scientists, in this talk I will address a more modest but nevertheless important task. Existing cloud labs necessitate the specification of every detail of the experimental protocols to be executed. In order to one day harness this potential, we have to first figure out how to generally optimize the parameterization of an experiment in the cloud lab setting. I'll now introduce our algorithm, protocol, that is designed to do just that, and demonstrate it using two different types of experiments: high-performance liquid chromatography and Multitoph spectrometry. Both of these experiment types have a number of adjustable parameters, and I will explain how we use protocol to optimize these parameters in a closed-loop fashion. The name protocol is short for Parallel Optimization for Cloud Laboratories, which I'll describe now. Protocol is an extension of the bound-based Bayesian optimization algorithm IMGPO. IMGPO is a purely serial method that notably comes with the theoretical guarantee of exponential convergence with respect to simple regret. Protocol itself is thus a Bayesian optimization algorithm. Bayesian optimization is a sequential strategy for optimizing black box functions. Such algorithms place a prior distribution over an objective and calculate a posterior distribution at the end of each iteration based on the results of algorithmically chosen function evaluations. For us, a function evaluation refers to an experiment to run in the cloud lab, and what is selected is a set of experimental settings. The idea is to observe a sequence of experiments where the settings for these experiments converge towards an optimal setting. We use Gaussian processes to represent the prior and posterior distributions, and our selection routine is specialized for the cloud lab and incorporates the upper confidence bound of the Gaussian process. It is specialized in two ways. First, protocol will choose up to as many experiments to run in parallel as is possible. The second is that the algorithm can be updated with the completion of any particular experiment. Thus, when one experiment completes, there is no need to wait before launching another. To get a better sense for how the algorithm works, let's go through a quick example. This diagram represents an experiment that has a single parameter, given by the x-axis. Protocol finds the setting of this parameter that leads to the best experimental result. For the sake of clarity, I've denoted the optimal setting with a blue star. The tree that lies above the x-axis represents experiments that protocol can choose to evaluate. The nodes correspond to experimental settings according to where they lie along the x-axis. The connectedness of the tree illustrates the deterministic method by which the algorithm is forced to explore the unknown parameter space. As more experiments are conducted, the tree will grow, where the separation between adjacent nodes will become finer and finer. This can be seen if we skip ahead by a few iterations. At the end of each iteration, protocol chooses a subset of experiments given by currently unevaluated nodes in the tree. When deciding which experiments to select, it considers previous results obtained earlier, an upper confidence bound for the unevaluated experiments, as well as the degree of exploration that has occurred in the space around a particular parameterization. After an experiment is conducted, new possible experiments are added to the tree by growing edges in the space surrounding the completed experiment. In the end, protocol converges to the optimal parameter setting, which is seen by the way that the depth of the tree is greatest near the blue star. Let's now apply protocol to some real data. I'll first show off protocol in what I call a simulated cloud lab. By simulated, I mean that the cloud lab environment is simulated. The data is quite real. It comes from two sets of Multitolf spectrometry experiments. Multitolf is an analytical technique that allows us to separate and specify proteins that are present within a complex mixture. By vaporizing a sample using a laser and measuring the flow of the vaporized ions through a flight tube, a detector can measure this signal and produce a spectrum, where different peaks correspond to different components of the mixture. When performing Multitolf spectrometry, it is common to first perform a brute force parameter sweep in order to identify settings that produce the highest quality spectrum. We use data from two such parameter sweeps over 4 Multitolf parameters. The samples included native chymotrypsin as well as a chymotrypsin polymer conjugate, and the goal is to find the parameter settings that lead to the best signal for each. The biological context for these experiments is to develop a chymotrypsin enzyme replacement therapy. While protocol is agnostic to this application, I just say this to emphasize how the optimization problem handled by protocol can be an important first step towards such a goal. Measurements such as peak height, width, or the signal-to-noise ratio are used to assess a spectrum's quality. These plots show the ground truth values of these measurements on one of the two datasets and show that they form generally complex patterns. In our experiments, we optimize for each of these measurements independently, as well as for two combinations of them. We compare protocol to a few other standard Bayesian optimization methods. We simulate the cloud lab by allowing each method to select up to 4 experiments at a time, corresponding to a realistic level of parallelization used in a real cloud lab setting. When an experiment is selected, the corresponding model is updated with the ground truth value for the chosen experiment. We allowed each method a budget of 25 experiments. We find that protocol identifies the best experimental parameter settings in almost every circumstance. These tables show the percentage of trials where each method identified the best parameter setting for each measurement. Since protocol uses a deterministic method to explore the parameter space, it has no variability in performance, which is why it takes only value 100 or 0. That it is 100% in 9 out of the 10 optimization tasks we tried indicates that it was effective at optimizing the parameters that govern these experiments. The remaining methods rely on an initial training set. We randomly selected small batches to serve as training sets for these methods, and repeated the procedure 100 times using different starting batches. As a result, these alternative Bayesian optimization approaches identified the optimal configuration much less frequently. Another consideration is how many experiments are necessary to identify optimal parameter settings. We find that protocol finds the optimal setting most quickly. For simplicity, shown here is only the peak height measurement, though others follow similarly. With the native chymotrypsin data, protocol required only 11 experiments to identify the optimal setting, and with the polymer conjugate, 15 experiments. This is many fewer than the 120 experiments that were ran in the brute force grid search that generated these data, which indicates that protocol can be a more efficient means of identifying parameter settings. All others require, on average, more than the 25 experiment limit. As a final point with our synthetic cloud lab analyses, we find that Protocol's deterministic exploration scheme adequately surveys the unknown parameter space and effectively avoids biases present in methods that require training data. These figures show the true peak heights associated with each experiment in the polymer conjugate data. The x-axis enumerates the 120 experiments, where nearby points correspond to similarly parameterized experiments. Red markings correspond to experiments selected by each method. In the case of Protocol, we see that the red is spread throughout and that the optimum was evaluated, even though the first experiment denoted with an X is far away from optimal. In the case of the more traditional GPUCB algorithm, we see that the method's ability to survey the parameter space is influenced by the initial training set. If a training instance happened to be near optimal, then the method finds the optimal parameterization, shown in the middle, but does not adequately explore the space when this is not the case, shown on the right. I'll now describe results where we use Protocol in a real cloud lab setting. Using Emerald Cloud Labs, a company located in South San Francisco who has partnered with CMU to help bring automated science into academia, we use Protocol to optimize a high-performance liquid chromatography experiment. HPLC is an analytical technique used to separate and identify components in a liquid mixture. As with MALDI-TOF, it has a number of highly technical parameters that can vary and influence the resulting spectrum. In our experiments, we varied 6 parameters, making this a more challenging task. We used HPLC to separate a 3-component organic solution. Thus, unlike with the MALDI-TOF experiment, where we wanted to optimize the signal of a single peak, here we want to resolve the signal of multiple peaks. We use peak resolution to qualify the resulting spectra. Essentially, spectra with peaks that are well separated, tall, and narrow will have high resolution. Since we use a 3-component solution, we want to find 3 highly resolved peaks. Due to limited time, we were only able to complete 18 HPLC experiments on the Cloud Lab, a modest number given the 6-dimensional search space. Here, I have shown the first experiment that was selected by Protocol, as well as the experiment with highest resolution, according to ECL's peak picking software. There is actually an improvement. There are now 3 peaks, and the peaks are more separated than in the initial spectrum. However, this highest resolution spectrum is clearly noisy, and it's not unreasonable to wonder if these peaks correspond to our sample. In addition to using Protocol, we also ran 18 experiments where we selected parameter settings using Latin hypercube sampling. Unlike Protocol, which dynamically chooses experiments in real time based on previous results, Latin hypercube sampling is a near-random way to specify a number of experimental settings in advance, where they are constrained to be sufficiently different from each other. To our surprise, one of these experiments yielded the spectrum on the right, which we believe is a valid, highly resolved spectrum. This led us to wonder, should we really expect Protocol to be outperformed by a near-random method? We don't think so. We came to this conclusion by running a simulation using the data that we generated on the Cloud Lab. We trained a regression model using the generated data, and then used this model to make predictions on 500 other Latin hypercube samples. If Latin hypercube sampling is expected to be better than Protocol, then these simulated experiments should be predicted to have higher resolution than those obtained with Protocol. However, we see that the predictions are more or less similar. None of the top 3 predictions, on average, surpass results obtained with Protocol, and the overall average favors Protocol also. So we think that this Latin hypercube result was unexpected and due to chance. A clearer takeaway is that Protocol needed more than 18 experiments to fully optimize a 6-parameter HPLC experiment in the Cloud Lab. Still, these are some of the first experiments where we've remotely generated our own real data using the Cloud Lab by making experimental decisions entirely through an AI-driven algorithm. There's more work to be done, but I think that these are some of the first steps towards a larger goal of automated closed-loop science. To quickly summarize, in this talk I described how cloud laboratories facilitate closed-loop science and how this addresses issues of inefficiency and access to resources that are prevalent in traditional experimental research settings. In order to take advantage of all the Cloud Lab has to offer, we need to be able to optimize experimental parameters that govern any experiment type. To this end, we developed Protocol, which is designed to tackle this task by taking advantage of the unique capabilities of a cloud lab. In a synthetic cloud lab setting, I showed how Protocol is superior to traditional Bayesian optimization techniques at optimizing 4 parameters using 2 MALDI-TOF datasets. Finally, in a real cloud lab setting, we showed progress made by Protocol towards optimizing 6 HPLC parameters and believe there is more work to be done. If you would like to try Protocol yourself, it is available on GitHub as both a standalone Python version as well as an R-Shiny app. Please give it a try and let us know what you think. With that, I'd like to once again acknowledge my co-authors, Ji-Yoon Gong and Chris Langmead. I'd like to acknowledge Dr. Alan Russell and Bibi Fatima Kotbayeva, who provided us with the MultiTOF data. I'd like to especially thank Emerald Cloud Labs, who provided us access to their Cloud Lab environment, and their whole team, who has been extremely helpful. Finally, I'd like to acknowledge funding through the Computational Biology Department at CMU, as well as through the NIH. With that, I am now happy to take any questions.